Why, hello! Today we're going to be exploring the wonderful world of titrations. Specifically, we're going to be asking ourselves if we're starting with a 100 milliliter solution of 0.1 molar CH3COOH, acetic acid, and we titrate in 0.2 molar sodium hydroxide, NaOH, what will be the pH at the equivalence point at 25 degrees Celsius? Let's get to it. So anytime you have a titration, that is, anytime you have a solution that's an acid or a base, and you add in a strong base or a strong acid, respectively, you're looking at a titration. And quantitatively, to evaluate these, when in doubt, is it out. We're going to use an ICF table. So the key to any titration is first writing out the reaction. We have here NaOH, sodium hydroxide. But does it matter if we use NaOH or KOH or CSOH, at least from a quantitative standpoint? No. This Na plus here is just there to counterbalance the hydroxide. So I personally like to simplify these before writing out the reaction. I'm just going to cross out the Na plus because it's just going to be negligible in terms of the pH of the solution. What's really going to be doing the reaction here is the hydroxide part of that. Okay, so sodium hydroxide, a strong base, it's going to be dissociated completely. It's the hydroxides that are really going to be reacting here. So then writing out our reaction, it's a breeze. We're just going to write out, we've got our acetic acid, so that's CH3COOH, and we're going to react it with our hydroxide. And what does hydroxide do anytime it encounters an acid? Well, it takes protons. A little bit of protons? Nay, a lot of protons. Strong acids and strong bases are strong because when they react, they go all out. They react completely. So we're not going to use an equilibrium arrow. Oh no. We're going to use a full-headed arrow because this reaction will go to completion until we use up our limiting reagent. So the hydroxide is going to grab protons from this. So it's going to turn the acetic acid into CH3COO minus, and it's going to itself turn into water. Okay, so because we have a full-headed arrow, this is not an ICE table, this is an ICF table. And ICF tables are, well, subjectively a little bit easier to work with than ICE tables because they reliably react to completion. But there's two important things that we need to keep in mind when we use an ICF table. First is the units. Whereas ICE tables use molarity, ICF tables use moles. Super duper important. So that's consideration number one. Let's get that out of the way. Let's figure out the moles of everything involved here. So we can use the relationship that moles are equal to molarity times volume in liters. So in this particular case, we've got 0.1 molar CH3COOH, and our volume is 100 milliliters, so we'll divide that by 1,000 to get 0.1 liters. Multiply these two together, and we end up getting that there are 0.01 mole of the CH3COOH. Okay, so I'm just going to plug that value into our ICF table. So this is 0.01. Great. Now then, you'll notice that we were only given the molarity of our sodium hydroxide. We weren't given the volume. Well, that's not really a big deal because with an equivalence point, what's the definition of an equivalence point? Well, it's when you have an equivalent number of moles. So actually, just by knowing that there's 0.01 mole of acetic acid, I know that we're adding in 0.1 mole of hydroxide to completely neutralize our weak acid. Over here, this is 0. And H2O, we don't care. It's not going to be factoring in. We're going to assume that the change in water is negligible compared to the overall solution. Okay, so thing number one that's different from an ICE table is that we have to use moles, not molarity. Thing number two is, with an ICF table, with a titration, when these things go, they go all out. So in order to figure out our F line, our final line, we have to find the limiting reagent. Pretty easy to do because it's a 1-to-1 ratio of everything. So, which one of these is the limiting reagent? Trick question. They both are. So these are going to react completely with each other, and they're actually going to be completely react when it's all said and done. Meanwhile, on the product side, we're going to be gaining 0.01 mole of acetate. So we're left with 0, 0, and 0.01 mole of acetate. Okay, so we're roughly halfway done with the problem. We know that once this neutralization reaction takes place, we're left with 0.01 mole of acetate. Where do we go from there? Well, we have to ask ourselves, what is acetate? What is CH3COO minus? We know it's the conjugate base of a weak acid. It's the conjugate base of acetic acid. Anytime we want to solve for the pH of a weak acid or a weak base solution, in this case, what do we have to do? When in doubt, ice it out. So there are 2 tables involved in this problem. Well, let's get to it. Let's do that second table right now. Okie dokie. So we've got 0.067 molar of the acetate. Let's go through and do our ICE table. Water, we don't care. Remember, there's no acetic acid or no hydroxide present in the solution initially because they were all completely neutralized during the titration. Our change, well, with an ICE table, we don't know the change here. So it's going to be minus x. This is going to be plus x, and this is going to be plus x. 0 plus x is x, 0 plus x is x, and 0.067 minus x is 0.067 minus x. Okay, so we're very close. We need an equilibrium expression. Quick thing to note, we were given the Ka of acetic acid, but this reaction that we're looking at here, this is the base hydrolysis of the conjugate base acetate. So what do? We don't need, well, we can't use a Ka for this. We need to find the Kb of this, the conjugate base. Fear not, because we have the relationship that for any conjugate weak acid, weak base pair, Ka of the acid times Kb of the conjugate base equals Kw, the autoionization constant of water. So with that information, we can solve for the Kb, then we'll have the equilibrium constant that we need for this particular reaction. Let's do just that. So Ka is 1.8 times 10 to the negative 5th. We're trying to solve for Kb, and Kw at 25 degrees Celsius is 1 times 10 to the negative 14th. So we'll divide both sides by the Ka, 1.8 times 10 to the negative 5th, and we'll end up getting that the Kb that we'll use for this reaction is 5.56 times 10 to the negative 10th. Okay, now we have everything we need to write our equilibrium expression, plug in our values, and get an answer to this problem. So let's do just that. My, what a journey it's been. We've done our ICF table, we've done our ICE table, we figured out what our Kb is. We're so close. Let's just write out our equilibrium expression, plug in, solve, and enjoy. So our equilibrium expression, products over reactants. So Kb is equal to the concentration of CH3COOH times the concentration of hydroxide all over the concentration of acetate. Remember, we don't include liquids in our equilibrium expression. Okay, fantastic. Let's plug in our values and let's solve. So our Kb is 5.56 times 10 to the negative 10th. That's going to be equal to, this is x, so we can just put in x squared over. And remember, there's a nice little shortcut that we can take here. Our K is 5.56 times 10 to the negative 10th. That's much smaller than our baseline for being able to use a nice little shortcut. Remember, any K that's on order of 10 to the negative 5th or less, we can assume that this change is negligible compared to the initial amount that we had. So we're just going to take this and drop it because we don't need it. So we'll put in 0.067 right here. We'll multiply the 0.067 through, and what we'll end up getting is 3.73 times 10 to the negative 11th is equal to x squared. Okay, we'll take the square root of both sides, and we'll end up getting that x is equal to 6.11 times 10 to the negative 6th. Okay, so now we finally know what our x is. And now we have to ask ourselves, what does x represent? It's the concentration of hydroxide. So if we take the negative log base 10 of this, we're not getting the pH, we're getting the pOH. So if we take the negative log base 10 of this value, we'll end up getting that the pOH is equal to 5.2. And then finally, to finish off this problem, at 25 degrees Celsius, pH plus pOH equals 14. So we're going to subtract this value from 14, and we'll end up getting that the pH of the solution is equal to 8.8. And voila, we are done with this. Okay. It's been quite a journey getting to our pH, but hopefully all of those steps made sense. With titrations, you always use ICF tables. With weak acids or weak bases, you always use ICE tables. And we need to make sure that we're using the correct units and that we're always using the correct equilibrium constant, be it Ka or Kb in acid-base chemistry. Finally, let's just compare what we know about weak acid strong base titrations with the answer we arrived at to make sure that our answer makes sense. So if we're titrating a weak acid with a strong base, we start with an acidic pH, and then we go through this zone where the pH doesn't change super appreciably. Why is that? Well, as we're adding in the strong base, we're using up our weak acid component, and we're forming the conjugate weak base. And as long as that conjugate weak acid, weak base exists together in appreciable concentrations, we get a buffer. So we go through this buffer zone where the pH does not change too appreciably, but then we reach a point, where the pH spikes up and then eventually ends up just being very, very basic. So what is that point where it spikes up? Well, that's when we've about used up all of our weak acid. So it's right around the equivalence point. And remember, you can always find the equivalence point on a titration curve by looking for that vertical spike or plunge if we were titrating a weak base with a strong acid, or actually just a base with an acid in general. So we can see here, if we look at this, the equivalence point for a weak acid strong base titration should be basic, because once we've used up all the weak acid, all we're left with is the conjugate base. So our pH should be above 7, and indeed it is. Great, that checks out. We're good to go.